Assalamualaikum. My name is Muhammad Hanif bin Zulkifli, Nometric AD210086. So, for the introduction, implants are medical devices that are placed inside or on the body to replace or support damaged tissue. They are commonly used in areas like orthopedics, dentistry, and cardiovascular treatment. However, traditional materials such as metals and non-biodegradable polymers can cause complications and sometimes require a second surgery to remove them. To overcome this, tissue engineering has been developed. It combines biology, material science, and engineering to create biological substitutes that can help repair or regenerate damaged tissue. In this approach, scaffolds are very important because they provide support for cells to grow and form new tissue. Because of this, biodegradable polymers like PLA, PGA, and PCL are getting more attention. These materials can safely degrade inside the body over time, which reduce the need for additional surgery and help support tissue regeneration. So for the importance of the biodegradable polymers can safely degrade inside the human body over time, which is very important in a biomedical application. One of the main advantages is that they eliminate the need for a second surgery, so this reduces both patient risk and healthcare costs. Example of these materials include PLA and PGA. Uh, These polymers can also be engineered to control their degradation rate and at the same time support tissue regeneration. Because of these properties, they are widely used in temporary implants and also in drug delivery system. So for the problem with metallic implants, although metal implants such as titanium and stainless steel are widely used because of their high strength and durability, they also have several limitations. One of the main issues is corrosion and the generation of wear debris, which can affect surrounding tissue. Another important problem is stress shielding, where the implant takes too much load and cause the surrounding bone to weaken over time. In addition, these implants are permanent and may require another surgery for removal or replacement, uh, which can increase both patient discomfort and medical costs. In some cases, immune reaction or even implant failure can also occur. So for the tissue engineering scaffold are very important in regenerative medicine because they provide a temporary three-dimensional structure that support cell attachment, growth, and tissue formation. This scaffold also mimic the natural extracellular matrix, which allow cells to grow, multiply, and differentiate more effectively. They are widely used in applications such as bone repair, cartilage regeneration, and skin tissue engineering. Therefore, the development of good scaffold materials and design is very important to improve tissue repair outcomes and support functional recovery.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Firdaus bin Syam Simon, CD220084. So for the fundamentals of biodegradable polymers, biodegradable polymers are material that can naturally break down after completing their function in the body. In tissue engineering, these materials are very useful because they can act as temporary scaffolds for damaged tissue. The scaffold works as support structure for the cells. It allows cells to attach, grow, and form new tissue. As the natural tissue start to regenerate, the scaffold will slowly degrade and replaced by the body's own tissue. So one of the advantages of the biodegradable polymers is that they can reduce the need for a second surgery to remove the implant. This is because the material is designed to degrade naturally after healing. However, the polymer must meet several important requirements. It must have good biocompatibility, meaning it should be safe and not cause harmful reaction in the body. Also, it needs suitable mechanical strength to support the tissue during healing. Besides that, the degradation rate must be controlled and the degradation products should be safe and non-toxic. So if polymer degrades too quickly, it may lose strength before the tissue fully recovers, but it degrades too slowly, it may remain in the body longer than needed. Therefore, choosing the right biodegradable polymer is very important. Next, the common biodegradable polymer used in tissue engineering. The first one is PLA or polylactic acid. PLA has good strength and is commonly used for bone scaffolds and sutures, but it can be brittle. The second one is PCL, polycaprolactone. PCL is flexible and has a slow degradation rate, so it's suitable for long-term scaffold application. The third one is PGA, polyglycolic acid. PGA has high strength and degrades quickly. However, because it can degrade fast, it may lose mechanical supports too early. Next is PLGA, which is the combination of PLA and PGA. The advantage of PLGA is that its degradation rate can be adjusted by changing the ratio of lactic acid and glycolic acid. Lastly, chitosan is a natural biodegradable polymer. It is biocompatible, biodegradable, and antimicrobial, which makes it suitable for wound healing and tissue regeneration. So these polymers can degrade through several mechanisms. Hydrolytic degradation happens when water breaks the polymer chains. Enzymatic degradations happen when the enzymes in the body break down the polymer. Bulk degradation means the degradation occurs throughout the whole material, while surface erosion means degradation mainly happens at the outer surface. So overall, the selection of polymer depends on tissue type, required mechanical strength, degradation rate, and biocompatibility.
Okay, Assalamualaikum warahmatullahi. My name is Fakhdam Razaki and I will talk about literature review. So, from a literature review, biodegradable material have become an important alternative to conventional permanent implant due to their ability to provide temporary support and gradually degrade after tissue recovery. Traditional implant materials such as metal, ceramics, and non-degradable polymer may cause long-term issue during inflammation, stress shielding, and additional removal surgery. From 2010 to 2022, research has focused on improving biodegradable polymers for applications in bone tissue engineering, cartilage regeneration and cardiovascular implant, drug delivery, and skin tissue engineering. Okay, next, which is major biomedical application, which we have three, which is bone tissue engineering, cartilage regeneration, and cardiovascular implant. For bone tissue, it is a temporary support for bone defects. A 3D printed porous scaffold improve vascularization and bone growth. Cartilage regeneration support chondrocyte growth and extracellular matrix formation. Biomimetic scaffold produced using electrospinning and bioprinting. For cardiovascular implant, biodegradable stent and vascular scaffold reduces long-term complication associated with permanent implant, as you can see from the example, which is a bone scaffold, cartilage scaffold, and biodegradable stent. Okay, moving on to the next slide, which is additional application. There's two additional application, which is drug delivery implant, which is control releases of drug, proteins, and growth factor. PLGA, PLA, and PGL commonly used. Nanotechnology improve targeting and release efficiency. For skin tissue engineering, used for wound healing and artificial skin substitute, which issues like natural polymers such as collagen, chitosan, and gelatin. Recent development, which is electrospun nanofiber and antibacterial bioactive scaffold. As you can see from the picture, this is a example of both drug delivery and skin tissue engineering. For drug delivery is the drug delivery implant and the skin scaffold.
Hi, I'm Muhammad Dayat bin Sarudin and I'll be presenting results and discussion. So for the advantages and disadvantages, a critical evaluation of biodegradable polymers PLA, PGA, PLGA, and PCL in implants and tissue engineering, weighing clinical benefits against material limitations. Yeah, for example, biocompatibility and non-toxicity, non-secondary removal surgery, and while the advantages are mechanical limitations, degradation, viability. So for the future directions and challenges, biodegradable polymers hold transformative promise for next generation implants and tissue engineering, overcoming current barriers in manufacturing, clinical translation, and material innovation will define the future of biomedical polymer science. First one is manufacturing and scalability. Challenges in scaling the biodegradable polymer fabrication for clinical grade production, maintaining batch consistency, sterility standards, and cost-effective manufacturing. As we know, for us to mass produce it, it will cost a lot of money. So for the time being, it is quite scarce. And next is clinical translation hurdles. Regulatory approval pathway long terms in vivo. It takes a long time for us to get clinical approval recommendation and starting trials. And next one is emerging research and innovation. Smart stimuli responsive polymers, nanocomposite scaffolds, 4D printing, generative active matrices, and AI-driven material design represents the cutting edge of biodegradable implant research and tissue engineering advancement.
For the conclusion, biodegradable polymers are promising alternative to conventional metallic implants. Materials such as PLA, PGA, PCL, PLGA, and chitosan are widely used in biomedical and tissue engineering applications. This material can degrade naturally in the body, eliminating the need for secondary removal surgery. Biodegradable polymers support tissue regeneration and improve patient recovery. They have applications in bone tissue engineering, cartilage repair, drug delivery system, cardiovascular implants, and skin tissue engineering. Despite the advantage, challenge remain in terms of mechanical strength, degradation control, and long-term biological performance. Recent developments Recent developments in material modification and advanced fabrication techniques have enhanced their effectiveness. Future research is expected to focus on smart biomaterials, multifunctional scaffolds, and personalized implant designs. Overall, biodegradable polymers have significant potential to improve healthcare outcomes and contribute to sustainable biomedical solutions.